So Dr. Ali Rogani is back again. So Dr. Rogani received his PhD in geotechnical engineering from Canadian Rail Research Laboratory at University of Alberta. He is a licensed professional engineer in Ontario and has published more than 20 peer-reviewed journals, conference papers, and technical reports. Welcome, Ali Reza.
Evan, can you confirm if you see my screen?
Yeah, looks good.
Okay, perfect. So good morning or good afternoon, everyone, depending where you are located. This presentation is about investigating the impact of frost heave and thaw softening on changing the vertical force at wheel-rail interface. And I am presenting on behalf of the project team, Dr. Yan Liu and Paul Burgess. If you had the chance to attend yesterday's meeting, we discussed about our long-term project about the effect of freeze-thaw cycle on the performance and safety of railway tracks. So both frost heave and thaw softening, they result in non-uniform deformation of track. It creates the irregularities that could affect the vertical force at wheel-rail interface. It degrades track geometry, and it shortens the service life of the components. So under the future climate, the freeze-thaw cycles are expected to become more frequent, and therefore this is important to investigate its impact on the safety and performance of railway track and to come up with mitigation measures. In this project, we looked at this phenomena from different point of view, and one of them that I'm going to present today was to look at its effect on the vertical force at wheel-rail interface and see if that might create an unsafe operating condition. So we had a 50-meter test section at one of Via Rail's line in Ontario. We monitored the track during the two freeze-thaw season, winter 2018-2019 and 2019-2020. We had different sensors at the test section, including shape arrays over the 50-meter section. You can see it here. There is another one on the other side of the track. Also, we had some geocubes installed at the center of the track to see if we can use those measurements to continuously and remotely monitor the track deformation. We also took the measurements. We used the total station surveys at the site to measure the absolute deformation of the of track surface. We used these measurements to develop a model in NUCARS and estimate how the vertical force at wheel-rail interface will change as the train goes through this section at different stages of FTC. We compared the output of the modeling with the AAR specification, which has a threshold on the minimum vertical load. So the minimum vertical load should be greater than the 10% of the static condition. Otherwise, there is a high risk of the derailments. So during our monitoring period, we had the two different winter. So I guess we discussed this yesterday. Just briefly explain that for those who did not attend the yesterday meeting. The 2020 was a mild winter. You see the freezing index that year was about 35% less than winter 2019. And also this difference in the winter severity, it was reflected in the track response. With 2019, we observed a shorter freezing period, shallower frost depths compared to winter 2019. Winter 2019, we observed about 1 meter frost depths, and in winter 2020, we observed about half a meter of frost depths. In addition, in 2020, we observed more freeze-thaw cycles. We observed about 4 intermittent freeze-thaw cycles compared to the 2019. And this type of winter that we observe in 2020, it is something that is expected to become the new normal under future climate. We took surface measurements at the site at the different timing at the different stages of FTC. Here in this plot, what you see is the temperature measurements at the thermistor that was located near the surface. It's about 1 foot below the track surface. And you can see the different stages of the freezing that is highlighted in the plot. The red dashed line are the time of our surveys, the total station surveys. And we had the first one in the June 2018 as a baseline measurement. For winter 2019, we had 3 measurements. First one was before the start of the freezing season. One was in the midst of the freezing season, and another one after the thawing. For winter 2020, we had 1 before freezing, 2 during the freezing, and 1 measurement towards the end of thawing season. So the measurements from this different time, they were used as an input into our simulation. And we'll look at how the train would perform as it goes through that type of profile. So here is our surface measurements using total station. The top 2 plots are for 2019 and south and north rail, and the bottom plots are for 2020. And for the 2019, as you can see, the largest frost heave is happening at the culvert location with about 17 millimeter of frost heave. And outside of the culvert, we observed that their average frost heave is about 7 millimeter. Another observation is that there is differential deformation over that 50-meter length of the track. And there is also differences between south rail and north rail, which is creating some cross-level issue. On the other hand, for 2020, we observed a similar pattern with the largest heave happen at the culvert location, with the amount very similar to 2019. However, outside of the culvert zone, we observed the average heave was about 2.5 millimeter, which was 1/3 of what we observed in 2019, which makes sense because in the 2020 we had a shorter freezing season and the frost penetrated less into the embankment. So it's basically showing that it's the frost heave outside of the culvert is less than the year before. However, this a smaller amount of the frost heave is creating a larger differential deformation. So when you look at this, these plots in terms of the differential deformation, 2020 is creating a worse condition than 2019. So we use these measurements. We imported this into the NUCARS, and we use the via rail passenger coach car model. We use the for the wheel rail geometry, we use that from NUCARS library. This is a tangent section, so this has a little effect to the results. And for the track geometry parameters, for gauge and alignment, we use data from the closest geometry measurements. And the only thing that we changed between our simulation was the changes in track profile that we measured through the total station, and the rest of the parameters, they stayed same between the simulations. Then we assume that the train is passing through the section at various speeds from 20 miles an hour to 100 miles an hour, and we extracted the forces at the wheel rail interface for each axle and for each of the side, for each wheel on the left and right side. Looking at the data for 2019, this is the variation of the forces at that as the train goes through that 50-meter test section, and the different colors, they are showing the different dates or different basically profile of the track. And as you can see, the minimum and the maximum force is happening within the culvert location, where the largest differential deformation is happening. And also the lowest value and the highest is recorded for the when the track was in the thawing stages. The value, when we compare the value with AAR specification, the minimum value is about 79% of the static load, which is well within the safe limits of the 10%. And the case for the track in thawing condition is creating that minimum value. The maximum value is about 20% higher than the static load. The AAR does not have any threshold on the maximum force, but it basically, the higher the force is, the higher stress is imposed on different track components, and it's reducing the service life of the track components. Repeating the same analysis for 2020, and again, different colors showing different time as the track goes through freeze-thaw cycle. Again, the worst combination is happening within the culvert zone, and actually the worst is the time that the track is in its thawing stage again. Again, for this one, when we compare it with the AR, we observe that this is basically within the safe limits. However, when we compare the values between 2020 and 2019, we observe that the numbers are worse. Again, still within the safe limits, but when we compare it in relative format with the year before, we see that 2020 is performing poorer than the 2019, which is again due to the larger differential deformation that is caused at the culvert, at the proximity of culvert location. If we look at it from for the various speed and also for different track condition, if we look at the minimum and maximum force, so we have repeated the simulation for a speed between 20 and 100, just to see if there's any resonance effect. And here are we're comparing the minimum and maximum force, and we see that the minimum force is happening when the track is in thawing condition, and also the maximum is again at the same dates at different location within the proximity of culvert. And as you can see, as we increase the speed of the train, these 2 points are getting further from each other, creating a higher delta value of the forces. Another way of looking at the effect of the speed, this is the vertical axis is showing the delta force, the difference between minimum and maximum, and this is for the track in frozen condition. So just to compare apple to apple, and we see that the speed has a clear effect, increasing that delta force. And again, the time that we observed the highest delta force was happening in 2020. So in conclusion, we did the simulation based on using the data collected from the test site. We observed that for this particular test section, the variation is within the safe limits. However, we observed some large differential deformation during the freezing season and also the thawing season. And it is especially important because as Kyle explained during his presentation, that's the time of the year that there is the track geometry measurement cannot work because of the presence of snow on the ground. So it is important to have a good monitoring system in place to pick up those deformation. Among different states of the track as it goes through FTC, the thawing, we found that the thawing is creating the worst combination, which is also known by the railway personnel. But here we have been able to quantify this. Winter 2020 created a worse operating condition than 2019, and this was the winter that we had a mild weather with more freeze-thaw cycle, which is going to be new normal under future climate. Again, I need to emphasize that this analysis was conducted on a test section in a high class 5 track, very well maintained track. So using, it doesn't mean that every track will be safe as it goes through winter or the tying stage. But to another track with a different class of track, with a different level of maintenance in a different weather environment might perform differently. So that's something that we need to keep in mind. And also, just to wrap as a final slide, I'd like to acknowledge Infrastructure Canada for providing funding for this project, VRL Canada for providing that data and facilitating field work, and my colleagues at NRC who supported this project. Thank you so much. And if there is any time, I would like to know your comments or questions.
Thank you, Dr. Rogani. We do have time for questions if anyone wants to. There's some very interesting analysis of data in there. I'll just start us off with a quick question. I'm just curious, why is there no upper force limit that AAR regulates? So they obviously regulate the lower force limit, but is there a particular reason? Because you did mention that it does cause damages to track materials.
Yeah, I think because that's not a safety issue, that's more a maintenance issue. That's probably they don't have a limit.
Okay, interesting.